Okay.
Welcome back, everyone. Welcome back. I am here joined by Bart from Poland. Just for the ones who just got in here, I'm Thea. I'm going to be chaperoning you on Nirvana stage. It really smells like Teen Spirit here. And I want to introduce our next speaker, Bart Szulc. And here's what we know what he wrote about himself. I've started my adventure with software development in quality assurance, at first running exploratory test sessions defining quality strategies for product, later got myself into test automation and performance testing. While I enjoy technology part of software development a lot, I know it's mostly about people. So I decided to get out of my comfort zone and instead of practicing automation, start teaching developers how to explore, automate, think about quality attributes of their software and product. Recently, jumped out of comfort zone yet again. Currently working as product engineering on distributed search system, where I try to balance my coding skills with DevOps and SRE. And here is chaos engineering bottom up. Word to you, Bart.
Oh yeah, thank you. Yes, my name is Bart Szulc. I'm not gonna tell much about myself. Probably already everything was said. And I'm gonna discuss chaos engineering bottom up because this is gonna be about chaos engineering as a team practice. So I'm looking at chaos engineering as something done by the team. So most of my experience is around developing or testing or assuring quality of standalone applications, big monoliths, products that you can install and run locally on your machine. But 4 years ago, the product that I'm currently working on started this migration from standalone and monolithic system to distributed system available in cloud. Because that's all we know, like all good monoliths eventually will end up in cloud. We knew that we can expect a lot of changes when it comes to the architecture of the system, but what we didn't really appreciate was all the changes that were happening on the team level or on the organizational level. When we were working on the monolith, we had like different roles. Those roles had different responsibilities, and the reason was that you couldn't have like a single person who was responsible for everything. Like there were just too much things to care about. So there were people responsible for coding in certain areas, people responsible for testing or assuring quality, people responsible for maintaining the product runs for our customers on production. But after we migrated or transitioned from the big monolith to distributed system, there was no longer this big chunk of software that had to be maintained by those different people and roles. Like this monolith got split into multiple smaller pieces, and this also meant that you no longer need many roles, you no longer need many responsibilities. And while I started working on the product as quality engineer, there are no longer quality engineers. We are all developers, and we just are responsible for many different things. We try to build, maintain, run our software with this mantra in mind. You build it, you run it, right? So how it works, like most of the times it works that we don't notice anything, right? Like our software, our microservice, part of the bigger system, runs on production, everything is fine, everything is green, we all sleep well. But in the case something goes wrong, in case our microservice that we develop, that we maintain, and that we run on production goes down, there won't be anyone else who is gonna wake up at night to fix it for you. This is you who is gonna get called. This is you who will need to wake up and address the issue very early in the morning. And you can ask, okay, so what's the big deal, right? Like with this mantra, I mean, what can go wrong in such a system where you have like multiple components talking to each other, and basically the state of the application is just like floating around between those components over reliable network, right? Like everything should work, because we know that for sure the distributed systems are easy to develop, are easy to maintain, right? And we have those truths of distributed systems. For instance, that network is reliable. Of course, I'm joking here, and everyone knows that distributed systems are very hard to maintain, very hard to comprehend, and there is a lot of problems that you can expect. Things that can go wrong, things that can wake you up at night if your system is running on production. Fortunately, all those problems have solutions, and we've been really good at finding solutions to those problems, packaging those solutions into libraries. So nowadays, it's just a matter of finding good library and introducing that library to your source code, right? So one could say, okay, so there used to be problems, but now those problems are gone with the new specialized libraries that give you a comfort and a kind of reliability that you need for, that you look for. Unfortunately, that's not the case, because you still see people at like very early morning hours trying to figure out what's going on with their systems on production. Like we still have incidents. So the question is like, what is failing if we are provided with those different tools, with those different solutions, with those libraries that should help us with fighting problems of distributed systems. And I think that part of the reason we still have incidents is the complexity of such systems and the butterfly effect. So you have a problem, you address it with a specialized solution, but fixing the problem causes another issue somewhere else in your distributed system. And what I mean by that, let me just give you like two examples. So this is like real world scenarios that happen in our product. The first one, we had an incident caused by a not following migration process. So we released a change. This change changed the structure of messages exchanged between services, and the new code of consumers was not prepared for handling old structured messages that were still floating around somewhere. So we decided that, okay, we need to be prepared for that kind of situation. So every time we are about to change structure of messages exchanged between services, we are gonna release those changes behind feature flags, and just like slowly switch from one implementation of a producer to another, implementation of consumer from one to another. But we knew that once we start releasing such changes behind feature flags, we are going to be dependent on some kind of feature flag service. And this is like yet another component that can fail in this distributed environment. But fortunately, there are caches, right? So if the component fails, we can always ask caches for the latest values for certain feature flags. But what we didn't know is that those caches won't be available when we construct new objects or initialize context for new nodes when they were like scaling up. So in situation where we experience like a heavy traffic and started scaling up our services, and for some reason feature flag service was not available, we couldn't really initiate the context, we couldn't start up nodes, and we failed, although it looked like we applied all the best practices. Another example, of course, like maybe in your product traffic is uniform, but in ours it's not. Like there are parts of day, parts of week where traffic is higher than in other parts. So we knew that we had to be prepared for spikes on load. So we decided like to just like analyze CPU utilization and spawn new nodes whenever we see an increase on CPU utilization on existing nodes. What we didn't know is that there was like small window of time when the CPU utilization could jump to high values when the new nodes were initialized. And this caused the orchestrating mechanisms to mark those new nodes as unhealthy, and they were basically never available to take the load from existing nodes. Meanwhile, the same orchestration mechanism decided to kill existing nodes because there are already new nodes being spun up. So we can basically recycle. So we ended up with a solution that was performing even worse with autoscaling that if we didn't have autoscaling set up this way. So you can look at those scenarios and say, okay, so we are doomed as developers working on distributed systems. Like there is no way you can anticipate all the different variations and how they can affect your system. And I would be kidding you if I said you can implement a system that is perfect and reliable all the time and prepared for all the different situations. That's definitely not the case. You need to be prepared to wake up at night and answer a call and find something new about your system that you never really anticipated, and it would be really hard to imagine while testing or proposing architecture. But we still can be a bit proactive about like finding those interesting scenarios. And this is why I'm talking to you about chaos engineering, because chaos engineering is a practice where via experimentation you can find those things that can fail for you on production before they fail on production, before you are waking up at night and need to address some issues. So if you ever seen the presentation on chaos engineering, you probably are aware of the cycle of experimentation that chaos engineering proposes. So basically, you start by defining steady state as some measurable output of a system that indicates normal behavior. You then hypothesize that the steady state will continue in both the control group and the experimental group. And later you introduce variables that reflect real-world event, like let's say like some kind of failure or malfunctioning network, etc., into the variable group. And you try to disprove the hypothesis by looking for a difference in steady state between the control group and the experimental group. Right? So it sounds easy. But when I first heard about that, I didn't really understand how to incorporate that practice into existing team practices. Like we try to run or develop our software or product in Scrum, in iterations. So where we should put this chaos engineering, where we should put the cycle in what we already do. And when I say we, I mean I and the team I'm part of decided to go with 5 phases. So basically, chaos engineering, like all the exercises that we do that are related to chaos engineering, are split into 5 phases. And those phases, or the work related to those phases, happen during standard development process. So there is no special sprint every once in a while where we focus only on reliability work, focus only on chaos engineering. Every once in a while we decide to run chaos engineering exercise in every sprint. We try to allocate some time for every single phase of the exercise. So what are the phases? The first one is design, right? So this is where you brainstorm with a team or with a group of people what kind of real scenario you want to experiment on, you want to replicate during chaos engineering session. We usually start with actors and expectations. So we are responsible for some kind of service. This service is used by a broader system, and there are people or other services that have some expectations toward us. And this helps us understand like what is the steady state that is expected by those actors. We also use that information to decide, okay, what is really necessary in order to meet those expectations, and what if something is missing, like how our service is going to react, how the whole system is going to react. So this helps us to come up with interesting scenarios to experiment with. Another source of scenarios are post-mortems. So we actively look at post-mortems that are published within our organization from other development teams. Basically, like saying, okay, we had this kind of incident, this thing failed, and this is what this is the impact it caused to our customers, and we are trying to assess whether similar situation could happen for our system, and is our system prepared or our service is prepared to handle them. The next phase is restrain. I think it's very important phase because it questions your intent behind running house engineering experiments. Like I started as a QA, so you could say that I was always there to break things, right? Like to find holes, gaps, and just prove that something doesn't work. And that's not the reason we are doing chaos engineering exercises, right? Like we are doing them to prove that our system can withstand certain conditions, turbulent conditions, but conditions that can happen on production. And we assume that we prepared our system, prepared the architecture to handle those conditions. So we are not there to, let's say, okay, we're gonna turn or kill the whole region and see if the system can handle that. Of course, it cannot, because we never implemented it in that way. And of course, this is not a good scenario for doing chaos engineering. So you in this phase, you're basically questioning whether there is really a value in checking the experiment that you chosen. Yeah, and this is also a place where we think about like backup plan. We know that things can fail. We know that we assume our system should withstand a certain scenario, but in case it doesn't, like how we are gonna react to that. The next phase is about preparation. So basically, we have a failure. We know what kind of experiment we want to run. Now it's just a matter of using available tool or creating new tool who is gonna create the failure within our system. It's also a phase where we look into observability. So we know that we want to observe steady state. In order to do that, we need to have some kind of charts. We need to have signals generated that are gonna tell us what is the current state of the system. And this is also a phase where we inform other parties that we are gonna experiment with our product, and that they need to be prepared that something can go down if things go not as planned. So let me stop here a bit, stop the boring part about like the theory and what kind of phases there are, and talk a bit about toys that you can use. Fortunately or not, this presentation is not about like all the tools that you can use, and because there are plenty of them. Basically, like most of the problems that you want to replicate, there is probably a tool that you can use for that reason. So the only problem you will have is how do you take the tool and inject it in part of your system, right? Like inject the poison in a particular place of your whole system. We have our product running on AWS, so we rely on Amazon System Manager. Basically, whenever there is a tool that we want to execute on a particular node, we just run a script, parameterize it, and just leave it to Amazon to execute the script on that machine. Of course, there might be multiple machines that we want to inject poison to. So we also have a kind of internal orchestrator that makes sure that whenever, for instance, new node of a class of nodes we want to break spawns up because of auto-scaling or some other reason, the poison is injected into the new node. But like having like a way of injecting poisons or creating failure in certain parts of your system is not good enough, because part of our engineering is also like monitoring the steady state, and you can't really monitor steady state if you are not getting any signals from your system. So if you are in the group that runs chaos engineering experiments against production, that's great, because probably your product is used by users, so you are getting a flow of signals that can tell you whether experiment is a success or not. But in case you don't have access to production, you can always like mimic real user interactions, and this is something that we do. Like we first start with staging, where we don't have real users, but we can mimic them, use the data that we gather from production to replicate standard user actions that are happening in production, and based on those actions generate signal and observe steady state on staging. Besides staging, we also have like dogfooding environment. So before experiments reach production, they also reach dogfooding environment. And here we have our internal users, because fortunately we have products that we use internally. So we have those internal users who are looking at those failures. Of course, they are not aware like what failed, etc. But we can use their actions to determine whether experiment was successful or not. Okay, so that was the preparation phase. The fourth phase is learning, or running and learning, right? So we have all the tools to execute experiment, and this is the place where we execute it, and when we trying to comprehend what is happening in the system, understand whether the system is working correctly, manage to certain conditions or not. We basically are verifying our hypothesis in this phase. So you cannot do that without proper monitoring and control, right? Like you need to keep an eye on, doesn't matter whether it's staging, whether it's dogfooding or production. You can't really do proper chaos engineering without proper monitor and control. Like otherwise, you are risking affecting whether internal users or external users that are paying for your product. So that's definitely not good. And even if things go wrong for you, right? So you assuming that your system can handle certain conditions, but if it can't, it's still something you can learn from. For instance, you can learn how well you react to problems, like how well you react as a team and as a system to incidents. So the first thing that we do as part of running our chaos engineering experiments, when they fail, we gather like information how long it took to, for instance, detect that we had a problem, respond to the problem, and recover from that. And this is something. Those are the times that we are trying to shorten. So in case there are problems on production, we are responding to them and recovering from them very quickly. And of course, once you monitor, you also control, right? So if things go really bad and your hypothesis was not verified and is causing harm to the system, is causing harm to your users, hopefully you have some kind of emergency shutdown or shut off, right? This is why we think about like backup plan in one of the phases. Like you need to be prepared that at any given step, something may not go according to your plan, and react to that. But if it does, like if something doesn't go according to your plan, this is also a great opportunity for you to learn, to understand something new about your product. So all those failures that we found during chaos engineering sessions were inputs for depth analysis as part of root cause analysis. So we were trying to understand what are the root causes of those problems that we've seen during chaos engineering experiments and address those root causes. The last but not least phase in our case is the improve. So we run the experiments, either they've proven that the hypothesis that we had was correct or not, and now we can address some action items based on the learnings. I think there are like four, or at least we see like four categories of action items. There are the minor action items, basically something that you can address in day, maybe up to 3 days, like changing a dashboard or adding extra monitoring that will help you understand what is going on with your system next time something like that happen. And this kind of work usually ends up for us in a Kanban backlog. So we have a person who is called disturbed, and this person is spending iteration working on the things that are in the Kanban backlog. So this will be probably those action items will be assigned to that person. There might be like some major improvements that require changes in architecture, for instance, and depending on how big they are, they may end up on the product backlog or on the product roadmap, and will need to be addressed by the whole team, because like we believe that efforts required to improve reliability are part of the product, are feature of a product. And I mean, lack of reliability can affect your users. So that's why that's one of the reasons why we treat it as part of product backlog. But they can also affect team, right? Like if you know that you have particular problems with your architecture, it's just a matter of time that people will be waken up during nights and address. We need to address real world incidents, and this is definitely gonna affect velocity of your team. The third category of improvements are root cause analysis. Sometimes we are able to perform root cause analysis as we engineering sessions. Often we need to understand what we failed, like what was the cause, like what was the root cause, and we do that in order to suggest valid improvement actions. And this is also is addressed by the whole team during a sprint, so it ends up in sprint backlog. And the last but not least, improvements are about the way we play chaos engineering. So we have like few plays that we try, and we always can improve them. And yeah, those improvements also attract us items on sprint backlog. So I was talking about like plays that we have for chaos engineering. So what are those plays? So far we've tried 3 things. Started with war games, then decided to change the war games a bit and came up with something we call Chaos Splash. And nowadays we run something called Chaos Day. Yeah, we basically were experimenting with different ways we can do chaos engineering sessions, and this is what we came up with. So what is the recipe for war games? So first of all, you need someone who is gonna drive like those sessions, the war game sessions. So we call that person a champion, and it's the responsibility of the champion to drive those sessions and also like assemble a team of individuals who are gonna work on the different phases that I mentioned earlier. So the team brainstorms on experiments, draft walkthroughs. So basically tries to understand what are the steps involved in a running experiment, and is there anything that can go wrong, and how we are gonna, like, what are our expectations, but also how we are gonna react in case something goes wrong. Like the team runs experiments, introduces a failure, monitors, verifies hypothesis, and if there was a failure, if a hypothesis was not verified, conducts post-incident review, agrees on action items, and does a retrospect on the whole play, basically like tries to improve it based on what they found while they were like playing war games. So this is basically what we end up with doing war games. So there is a group of individual who is running experiments against our system. When it comes to like time, how much time we need to run war games, it's about 5 to 6 hours total. So not that much time. So basically, it's a good cost to value ratio. You're spending 5-6 hours to learn a lot about how your system performs and whether you have some gaps that can be problematic once you are on production. And another thing that you gain from war games is that you improve operational skills of the participants, so of the group that works on war games. Unfortunately, we found that there are problems with war games, and those are the problems. Like the first problem is that once you are in the group, you apparently never leave. Like I think it's because like people are getting more and more experience with war games and the operational things. So it's easier for the team to delegate individuals like that are gonna do war games for them and not do any kind of rotation, because like those are the most those are the most senior people who are aware of what war games is, how to introduce failures, etc. What is house engineering. So let's always like put those people to do the play. I have seen like decline of creativity, and this is probably related to like keeping the same people in the group. Basically, like even like experiments started to be copy and pasted. So nothing new was generated, no new ideas for experiments was generated. Because no new ideas were generated, those people who were doing war games had stale view of the system. And your system is evolving, like there may be new message queue, there may be new service coming up. And if you are not pushing yourself to experiment with the new thing, you will always see the system as something that is probably not really reflecting what is happening on production. This caused minimal investment in scripts and tools. We didn't implement that many automation around chaos engineering, unfortunately. Once we had something, we just like reuse it. And another big problem with war games that we found is that you know exactly what's going to happen, or at least you suspect what's going to happen when you run an experiment. You know what is the failure, so you have some kind of expectations what can go wrong, and you are prepared to address them. When in reality, when incidents happen on production, you don't know what caused them. You need to figure out, based on available monitoring, based on available alerting, dashboards, etc., what is going on. So this part was definitely missing. Yeah, got frozen again. Okay, so we aware that the war games has its problems, decided to improve it a bit, and this is why we have Chaos Bash now. So Chaos Bash is a bit different than war games. Instead of having like just 2-3 individuals, we have 6 to 9 people involved. Instead of having like one team that experiments on the system, we have like we split those 6 to 9 people into 3 teams. So we have a bit of competition going on between the teams. Those teams work in brainstorm experiments in secret. So the other team is not aware what experiments are gonna be executed against system. It's the responsibility of the champion, of the Chaos Bash champion, to schedule Chaos Bash session and announce the session to all the people who will be or potentially could be affected. Like, for instance, if we are running the session against dogfooding environment, inform people who use our product internally. And within the session, we have like multiple iterations. We have those 3 teams, and those teams end up in different roles. So we call the role, we have like 3 roles, red, blue, and yellow. Red is responsible for running experiment. Blue is responsible for being on call. So if anything goes bad, there will be the ones who will need to figure out what went wrong and what is happening to the system and resolve a problem. and yellow is just there to observe both teams and take notes. So we have like objective view of what happened during the whole session. Teams change roles in each iteration, so everyone has a chance to run their experiment and learn from them, prove their hypothesis, but also everyone has a chance to become like a blue team and try to accident if there is any, and see how they perform. Okay, so how does it look like? So we have like those people in different roles. So we have red, we have blue, and we have yellow team. So the red team is responsible for running experiment. The blue team is there to guard the system, or at least like in case something goes wrong, fix the problem. And yellow is just to observe both teams and take notes, because most likely if anything goes wrong, those notes will be used to conduct post root cause analysis. Okay, so red team runs the experiment, and if everything goes well, the teams change their role. So the blue team becomes the red team and experiments on its own. Because there are like more people involved and we have those iterations, we tend to spend more time running Chaos Bash than war games, 12 to 14 hours in total to go through all the phases. But there are like a lot of good stuff coming out from Chaos Bash. First of all, competition fuels creativity. Sparks new scenarios. So we have like new experiment going on. Those new experiments require updated view of the system. So we are not afraid that we are just working on some view of architecture that is no longer relevant. There is a lot of teamwork going on. First of all, when designing experiment. Second of all, when you are as a blue team trying to figure out what is going on with the system if it fails. And how to restore its functions. And the yellow team ensures the rules are adhered. So there are no cheating. That whenever we try to fix problems, we are not relying on instinct, but rather on available documentation or run books. Still, there are problems with Chaos Bash. For instance, this us versus them mindset. This is something that comes from competition. So sometimes it can be a challenge to focus on proving that system can withstand, not breaking the systems on the other team has problems in recovering it. And we also noticed that blue team, instead of relying on alerting, is calling for information. So it's constantly checking what is the state of the system that is under exercise. So this is basically what happens. Like the red team is experimenting with the system. Nothing happens to the system, but still the blue team responsible for the system and knowing that they will need to fix any kind of problem if it arises, instead just checks everything, every dashboard that is out there to make sure they didn't miss anything. And this is a problem because and this is definitely a problem because on production you won't check the status of your system 24 hours, 7 days a week. You rely on alerting. So we decided to do a bit of change to the Chaos Bash, and the experiments can now run within longer time frame. And of course, like as a blue team, you could have monitored your system for, let's say, 90 minutes. But if the time frame is now 4 to 8 hours, no way you're gonna do that. So you start relying on alerts, and that's great. Okay, so how does chaos engineering works in nowadays when everything is done remotely, right? And we are working as remote teams. Basically, like Champion is still responsible for driving the sessions. What I do is I just like create 2 Zoom channels. two Slack channels and invite the yellow team, who are the observers, into both of those rooms. Like they will be, they are split between one and the other, and their responsibility is to take notes what is happening on those channels. Meanwhile, the blue team is there to react to potential problems. They appoint like a single person who is gonna be called whenever there are problems with experiment. They don't stand on the Zoom channel. They will join whenever there is a problem. They can resume their normal work. I mean, we don't want them to be occupied 4 to 8 hours just by looking at the other dashboards. The red team is for the whole duration on the Zoom channel, and they are experimenting with the system. Yellow team is taking notes whenever something happens. Of course, it's very important for the red team to tell up out loud what they are about to do. Like if there are any comments, they end up on the Slack channel. And if anything goes wrong, if the hypothesis is not verified, we have a problem, then fortunately, hopefully there is an alert, and it will notify the blue team to join their meetings and address the problem. This doesn't mean that the red team is not looking into what's going on to the system. We consider system like the software, but also the people, right? So if we expect that people will react somehow to a failure, then we need to check if this really happens, right? So the red team is responsible for the whole experiment from its beginning to the end. So they need to look that, for instance, problem is being resolved by the blue team. If it's not, they call it off. They need to run. They need to shut it down and restore state of the system. It's their responsibility to restore the state of the system. Meanwhile, you as a champion, you are just moving from one channel to another and just making sure that everyone is involved. Okay, the good thing about such chaos day, yeah, I mean everything good that comes from chaos bash, but also you test your anomaly detection, you test your alerting. There is no way the blue team is gonna continuously look at dashboards, so they need to rely on alert, and you can check whether those alerts are even fired whenever something is wrong. And you have also genuine surprise and stress experienced by the blue team. And this is really what is happening on production. This is really what is happening in real life. So it also helps us prepare ourselves for real world and real incidents. When it comes to problems, definitely like there is a lot of necessary investment, right? Like you need a lot of time and a lot of people. Sometimes it happens that the red teams forget about experiments. So they run experiment, forget about monitoring the side effects of the experiment, monitor the steady state, and just leave it up to the blue team. Most of the time, this definitely could work because blue team should be prepared to handle any kind of situations, but it's the red team responsibility to keep watch over experiments. And unfortunately, like the increased level of stress is also a problem because sometimes people may not be prepared for handling even not real incidents, and this can cause them a lot of pain. And this is something that we've noticed, like while running chaos days, that some people, for some people, it was really hard to work under stress when they were getting calls from like some systems saying that something is wrong, when they were pinged by their managers, when they were receiving SMS notifications, etc. They couldn't handle that. So nowadays we are thinking about like improving what we do as team, how we react to incidents, and also appoint a role in Chaos Day that we call incident manager. So that's gonna be the person who is gonna just direct other people who act in the blue role, so they just take some stress out of them, so they can focus on running or trying to comprehend what's going to the system and fix the system. Okay, so key takeaways. Yeah, I hope that I've shown that chaos engineering is really a team practice. You can't do it individually. You can't do it as a group. Otherwise, you would just lose the creativity that comes from like diversity and involving other people in the practice. Gamification definitely improves engagement. So we have like this competition between people and teams, but also yeah, and people are part of the system too. So this is also something that we learned while running chaos engineering. That is not enough to focus on the system itself, but also like you need to consider people and how they will react in stressful situations. Okay, if you have, yeah, this is those are the books that I suggest to go through if you want to do a follow up on chaos engineering and releasing reliable software. And that's it. Thank you.
Thank you very much, Bart. Brilliant presentation. Unfortunately, we're running a little bit over time here. So I have one question there in chat. Thomas Bloch is asking, what are the reasons within your organizations that you don't chaos engineer on production? If you don't mind, I would invite Thomas and you to go join the allocated Q&A area, and maybe you can discuss the question over there. How does that sound?
Yeah, that sounds good.
Awesome. Well, thank you very much, Bart, and thank you for watching. We will have a very, very short break, and then we'll continue.